Ishan. I am PhD student from IIT Tirupati, and this is a 10th session for the deep learning course. So today we have preponed it. That is, I'm going to take 2 sessions today and tomorrow as well. So today I will mostly talk about from the perspective of batch normalization and dropout, which are considered as a hyperparameters which we can control to improve our model training. So I will be going through some basic theory aspect and followed by code aspect, and then I will introduce you to one simple one tool which people use in practice. I might not able to show it today, but because I haven't set up the system, but I will show you a system called as MLflow, which you can use uh, for your training, for understanding the purpose of if you change parameters or any other stuff, how you can visualize them. Okay, so I will just introduce that concept to you, and followed by from tomorrow we will look at the sequence problem, that is for how sequence learning problem, it's a specific problem which we can use and from which the neural networks architecture like recurrent neural networks or the LSTMs, lot short uh, term memory, I think lot short term memory. So that is what we are going to look at for tomorrow class. Okay, so let me start sharing screen and just give me the aspect for that. Before that, do you, any of you, right? I think Nilamani and Shivkan, do you have any idea of what is batch normalization or dropout? You can type out in the chat section. Either as yes and no, or you can speak out also, because we are only two members are there. So any of you have any idea with respect to what we call as, let me take the black, batch normalization and dropout? Have you ever came across this kind of words with respect to it?
Yeah, actually, it is used to improve the efficiency, right?
Yes, kind of efficiency, but in what aspect? Efficiency, like epoch is make epoch, like for example, epoch is the word, is the hyperparameter which makes the model look at the data set again and again. So that is the purpose of epoch, right? Learning rate is the purpose. Learning rate is for uh, uh, to uh, to make the weights which the model is training to a certain constraint, like such that it should not grow too much, right? So that is certain purpose are there. But what about the batch normalization dropout? And it is mostly used from the perspective of CNN. It is used for other aspect also, but mostly it has been used from the perspective of CNNs, because we are dealing with the image data. Okay, okay, so let's see with respect to it how we can look into it. So let's talk about, before batch normalization, let's talk about something called as normalization, or you might heard the another term for it, which we call as standardization of the input, right? So let's assume um, that there is a data set, okay, a kind of mobile data set. So you have mobile number 1, 2, 3, 4, 5, like n number of mobile data set, and for each mobile you have some feature 1, feature 2, feature 3, like that, some d features, right? And you have certain numbers here, certain numbers for defining each of the features, right? So now there's a high probability chance that the for the particular feature I might have the range in between, maybe let's say feature 1 is price, so I might have it as like 10k, 20k, okay, uh, 40k, kind of like that. This is one kind of feature. In another feature I might having let's number of cameras I have, so I might have 1, 2, 4, kind of like that, right? Another feature I might have where I need to see from the perspective of memory, right? So in there I can have, maybe in the case of 1 GB, 2 GB, or I can write as 1024 or 2048 KB in some range. So I will have certain features which are varying in a different feature space. Might be between 0 to 1, might be between 0 to 10, might be between 0 to 100, or maybe 1000, 10,000 to 50,000, like that, right? So I have features with varying different ranges are present to me, right? Now, there's a big problem with respect to if I have a data set with having multiple different ranges. What is that? That my model has to learn each features in a different scale, right? First of all, it has to learn all the features, and that too it has to learn from different scales, right? Somewhere in thousands, somewhere in tens, somewhere in maybe 0.1 to 0.1 to 0.5, like that, right? Now because of that, lot of variance come into picture. Okay, lot of variance come into picture where I can't plot the whole mobile data distribution in a single plot, like my model can't comprehend it. So what people have thought of, that let's standardize it to a certain range. So the standardize is mostly, so when we apply standardization of data, which we are now calling it as a normalization, also known as normalization, I want to keep all the data into a certain range. Okay, all data within a fixed range. That means I will convert my all data of with various ranges value. Maybe let's suppose between 0 to 1. I want to keep in this range only. Okay, now how to convert that? So to convert this to a standardization part, what I have to do is I will take let's go up a little bit. Uh, I will, maybe what I will do, this is my feature data, feature one data for all the mobiles I am having. Okay, so what I will take, I will take its mean and standard deviation. Mean, which is coming from like mu, and standard deviation, standard of is sigma. Okay, so I will calculate this one. So after calculating for each feature, what I need to do is I need to calculate mean for it. So normalization will come into as like xij norm, I can write it like this, and for xij, that is for particular instance for a particular feature, let's j is a feature, jth feature, and ith mobile. I will calculate it by subtracting it with its mean divided by its sigma, standard deviation. Okay, so I have standard deviation for j and sorry sigma for mean for j. That is for the particular feature I will extract its mean and standard deviation, and based on that I will calculate it. And mean, you know that how we can calculate, that is divide 1 by m. Let's say m is the number of mobiles, m is the number of mobiles. So it's pretty straightforward maths with respect to what we are doing here, right? Xij. So this is for mean, and if I want to find for standard deviation, I will take just the square root of the mean. So I will just add it as this 1 by m sigma I equal to 1 to m xij minus mu j square. So this is standard deviation I'm doing, right? So this is how I can identify for each feature that I am taking here. For each feature, I can standardize them into a particular range, that is in this case 0 to 1. So how I know that it's going to be 0 to 1? Because if you analyze, if you do manually and all, when you apply for this, you will generally create a normal distribution graph. Okay, so how normal distribution graph works is like in between where I have a peak there, here my mean will be 0. So here mean will be 0, and I have a standard deviation of unit standard deviation. So minus plus sigma minus sigma minus 2 sigma, say plus 2 sigma minus 2 sigma, kind of like that. Typical statistic concept is there. So when I apply normalization, all of my data will be come under similar distribution. When it's come to similar distribution, it's easy for my model to understand. So when all feature becomes similar type of distribution, my its model training become very easy. Okay. Okay, so now let's agree with the fact that the standardization is help us to put our data into a certain range. Okay, and that putting that range into us, it's help the model to it's for model training. If you're able to understand that, now let's see what will happen uh, if we don't have it. Okay, so if we have different weights to a different kind of features and also what will happen. So let's assume that I have weights. So let's say this one feature is one here, x1 x2 feature is like this, and now it is and I have certain values, and it is has been spread over a particular different kind of ranges. Okay, so it has been spread along x1 and x2. If I plot, it's spread across all this thing, and when I so that is before standardization or before normalization. And after applying after normalization, my data scope will be in similar to a kind of this thing. Let's assume for this part that it is between 0 to -2 2 kind of thing for x1 and x2. Okay, so instead of learning all this data with lot of variance, it has lot of variance, it comes down to this part where it has less variance. Okay, now what is the impact of this variance? So if variance means if I have a like my data somewhere it may be 1000 and one data point has 10,000, so my variance is quite of 9,000 is quite big, right? So here I'm not dealing with the 9,000 that big of difference. I'm dealing with my 0 0.5 0.7 in that kind of variance that is able to help me to understand. But if I don't keep it, so what will happen is, see, in a typical feed forward neural network or any neural network. Okay, so I have these three input, hidden and output layer, right? So what happens is I need to calculate, the model has to calculate its weights particularly on that. Okay, now suppose what happens, this delta 1 delta 2, sorry, w1 w2 is there. Now w1 is related to a value which has very high value, let's say price. So w1 dealing with high values. So if it is dealing with high values, its updation will also be according to that, right? But delta w2, it deals with very low values. So if I'm dealing with a very low value, so my updates with respect to weights is also not that much, because you can see is a proper correlation that if I'm dealing with something in the range of 0 to 10, the updates will be changing with respect according to that. Okay, but if I'm dealing in the range of thousands, the weights will also uh, positively correlate, and it will increase or decrease to in the order of thousands only. Okay, now when you're dealing with this in a typical neural network, what happens is the w1 might overshadow the w2, the second feature of the w2. Okay, because I have larger values in w1 compared to w2. Okay, because of that, if I have a feature with deals with a larger high value, it will prefer to learn those values compared to lower value. Okay, because it will consider that, okay, higher value means it might be related to that this is what I want to, and the my user is asking me to train, right? So the higher the values, the better. So that's why they're training the w1 much more better compared to w2, right? So to reduce that kind of differences or that bias, to reduce such bias, we do standard normalization. We perform normalization. Okay, so now So what we have seen, there is something called normalization, where we're trying to keep all the features of different ranges to a constraint of, let's say right now for 0 1. It can be others also. It doesn't need to be between 0 and 1 value, but standardized practice we usually do 0 to 1. Okay, now it helps us to reduce one bias also. Okay, so now that part is there. Now, so we can understand from the perspective of input. Okay, that means that I have an input and I have different features and I am putting them into a certain range. That is fine. Now the next question, natural question that we should ask is, what about the hidden representation, or what about the input, hidden input, right? So after training some data, I am also getting certain weights for these three variables, all right, highlighted in blue box. So I'm getting for that also. Can I apply normalization for that also? So that is the next question that we should ask. So the question will be, uh, we uh, we have standardized input, but what about hidden representation? Okay, so hidden representation here in this case means the weight vectors in the hidden layers. So uh, here the concept of normalization with respect to hidden weight vectors also come into picture. Okay, so same concept, like let's say here, uh, so okay, let's go here. So any weights here, we can have something called as pre-activation function and activation function. Okay, so here let's h1, h is belong to activation function and pre-activation belongs to a. So a is below and h is above, right? So that's how typically neuron is given to. So before entering the neuron, we are performing something called as pre-activation function. Some function will be there, and then after that we're converting, bringing non-linearity using the activation function with the help of tan h, relu, or the typical sigmoid neuron. Okay, so that we supposed to do, right? Now what happens, that what usually in practice happens is that they will take pre-activation values, so let's say a something, and it has some certain weights. So, and for each feature it has certain weights written here, right? The same procedure of calculating mean and sigma happens. Okay, and based on that I will get certain output within a certain range. Okay, that certain range is between 0 to 1 more, usually, and then I will pass it to the non-linearity, that is either a sigmoid, activation function, tan h, or relu. So I get this part. Okay, so this is passed to the activation function and I'll get certain value. Now, do we need to perform normalization even within the representation? So it comes back to the same argument, that the way I have, the way after normalization I am getting the normal distribution. This is called as normal distribution. Okay, and normal distribution is typically good for a training model to learn certain amount of patterns with respect to it. Same way, even with respect to the hidden layers also, I need to create this kind of representation. Okay, if I able to achieve this representation, which I can do with the help of normalization, I can achieve that. Okay, now once you're able to convince that, okay, so within a typical layer, within a typical neural network, I can standardize my input. This standardization is done. Even this standardization is also done. Okay. Now there's something called as batch normalization. Now batch normalization means, so if I'm passing and sorry. So what, now let's build on the concept of batch normalization. So what batch normalization do is, if you have attended previous sessions and earlier part, now we are dealing with, now when we are making a CNN, in that CNN we have dealt with something called a CIFARTN dataset or MNIST dataset. right? Now these data set consist of 60,000 images, and this data set maybe consist of um, maybe maybe 10k data, more than 10k images, something like, I'm not exactly sure, but these are quite big amount of numbers, right? I can't build I can't put all the 60,000 images into the my main memory directly, okay, because it is quite big. It may be in the ranges of MBs or GBs, right? So what I will do, I will pass batches of images to my model training. Okay, so I will train my model based on the batches. So for each epoch from the dataset, I will take batch wise images, and based on that I will try to train my model. Okay, so for each epoch, for each batch wise, till it completes, it traverses the whole dataset, I'll train my model, right? So that means I'm I'm breaking my dataset to small parts and trying to learn it, right? But the problem is, if I'm trying to learn it a small dataset, so how can I keep track of all this part, right? I might get, for different batches, I might get different weights or different values for that, right? So how should I deal with such variance? That's where the concept of normalization come into picture. That means after each batch, let's say batch of 16 images, okay, I'm training my model on 16 images, and my model is pretty big, so it will take some time to learn is 16 images. So based on that I will get certain weights. Okay, now weights can be anything in the order, right? So what I apply, I will just apply normalization on top of that, on these weights, and again I will go back to the training, where I will take new batch of 16 image, again I will get some weight, and again I will apply normalization, such that it will be in the range of 0 to 1, right? It will keep on changing with respect to it. Now once I'm doing this, uh, so what happens here is that, let's suppose I'm learning certain weights, and that weights are actually pretty good for me. Okay, so let's say at x iteration of a particular epoch, that means I'm at that point I learn certain weights, and I'm getting pretty good accuracy with respect to that, because after every learning of weights I'm applying the loss function, I will checking that how it is working with respect to weights, right? So that is a typical procedure. So when I'm doing this, I'm applying, I got the certain weights are pretty good, but I haven't checked the whole data. So obviously I can't be assured that weights are very good or not, because my, even though my loss has been reduced, and accuracy is being good, but still I need to check the other part of the data also, right? So that's why this multi uh, multiple changes in the weight because of batches, because of batches and normalization, or let's say right now batch normalization, because we have introduced the term now. So for a batch we are doing normalization, it will bring noise. Okay, and noise is something we need a lot during a typical deep learning network. So why noise is important? So why noise is important? Because it will our make our model robust. Okay, it will make our model much more robust with respect to it. So what do you mean by robustness here? So let's assume that, okay, now this is 16 cross 16 image, like 16 cross 6, say 4 cross 4, my bad, 16 pixel image is there, where the 3 is written here, right? So if I give this input, it might able to learn it, right? But what if I bring certain noise? So I may say that this part is not there, I just moved the certain part, or this part is not there. Okay, So still my model should be able to, if I give this kind of image where I have not is not looking like a 3, but still we know that intuitively that is 3, right? So model should also able to know that. So how it should know that? It should identify different kind of patterns, that it might look at this, there's a curve here, there's a curve here, there's no curve here, there's no curve here. So ideally it should come into class 3, right? So this is the kind of noise we are bringing, the noise that we have used. And here I'm putting blue here, blue circle. Okay, this noise we have bring into picture. So the nodes has to be able to learn this kind of thing, and this can be achieved using this noise, that is we are putting the empty spaces or some other data in on top of the 3. This will bring with respect to the normalization. This will come with the help of normalization. Okay, so that is the use for that, and that's why batch normalization, which is also considered as a regularizer. Okay, you might heard the term of regularizer in the terms of L2 norm kind of thing, right? So this is batch norm is also one type of regularizer, which the aim of a regularizer means that it should uh, make the model robust. That's the first point. The second point here is that it should not, it allows, it avoids overfitting. Now you know the overfitting of data, that overfitting in a typical model means I'm able to properly train on the particular on the whole training data, but when it comes to testing I'm not able to predict it properly, right? So that's our, to avoid overfitting we bring the normalization. So here batch normalization is one such idea with respect to it. Okay, now now let's let's see through code that how it actually works out in the typical in a typical real case scenario, right? So let me stop the sharing here, and let's go to the code as well. Okay, let's share the screen. Okay, now it's coming. Can you see my screen now? Yeah, I think you can see my screen now. Okay, so let's see how we can do with respect to the batch norm aspect. So what we have done, we have taken some few libraries like Torch for PyTorch, Matplotlib and NumPy for plotting, Torch Vision for basically downloading the data sets or transforming the data set into particular tensors and all that, and Torch, and then Optim is mostly for creating the neural network. Okay, and Seaborn is for plotting. Okay, so once we run this part, for dataset we are taking torchvision.dataset, and we are calling torchvision dataset MNIST. MNIST is the very famous dataset, which it's a handwritten number. So let me show you how it look like. I think here it will be much better. Okay, okay, then let me show you directly here. Okay, so it is like a 28 cross 28 image with 10 classes, that is 0 to 9, and it is written handwritten, and it's a grayscale. That means the background is black and only one scale is there, that is white here. So that's a grayscale data set. So typically this kind of MNIST data set we have it, and it's a very pretty much famous data set. So if you want to learn about CNN and anything, you should look out for MNIST and the CIFAR data set for your better understand or for your practices. Okay, so we are running this, and we are keeping this data into root of data folder. Okay, so we are downloading it for the training part. That's why I put train equal to 2 and download equal to 2. That means you have to download, and then you have to transform these image to tensors So you use transform.to tensor function to do that, because we are dealing with PyTorch. So you can see here in the files section of this batch norm, you can get this data. Okay, I will just share you this code as well. Just a minute. I'm just posting in the here. Okay, you can check this out in the meantime. Okay, so now we have taken the data set from here. Now we are defining the batch sizes for, that means 4 images at a time we are going to look at. Now we are creating a variable called train loader, where using torch.utility we are loading the with the help of data loader, we are loading the 4 images from the train set, which is from the MNIST train set, which batch size equal to 4, and we are taking randomly at a time 4 images, right? That's why for shuffle equal to true we have done. So once you run this part as well, um, this and then after getting the train loader, you creating an object called iterator to iterate with all the 4 images. For do that, you're creating a data iter object which will iterate through all the 4 batch of train loader, and from that it will extract images, what is the image and what its particular label will be like, right? And it will showing the shape of that image, that is the combination of 4 images. So it is shown as 4 with channel 1, because it's a grayscale, with 28 cross 28. 28 cross 28 is the width and height of the image, right? So for particular one image, it is showing the shape, that is 1 cross 28 cross 28, that is one channel with 28 cross 28 with an image, and the label is label of that image, particular image is 1, right? Maybe the handwritten number will be 1 here. So this is for def IM show and def show batches. It's for uh, showing a particular single image or a grid of images, right? So these we have discussed in earlier part, but you can take some time later to check it. In overall, what we are doing is, in IM show we are creating a figure with the batch size of 4 into 4. That means we are taking each image from the batch size and we are plotting it together. Okay, now we are also transposing it to a certain range, because this one is written as number of channels, width and height, but we usually see in the axis of x, y and z. So the z axis here is keeping here as 0, that is the last point. Width and height 1 and 2 is written as first, right? So that's why we transport the image and we're showing it. For batch, with the torch vision.utility, we are making a grid of images, we are placing them one side by side, and then we are calling the IMShow function. So this is how it will look like. So if I run this, so this is 4 images, 7119. So it has shown as output as labels also, if you can see in the top, if you can see my cursor here, so that is 7119. This is the actual image, 4 images on which we are going to deal with. Okay, so this is our data set. Now let's deal with normalization. So for that we haven't taken any architecture, we have taken simple neural network, where we have using the torch.nn, we are creating a classifier, and we are merging all the layers using nn.sequential, where we have a one single neuron layer with 784 input. That means our width and height is 28 cross 28, right? So if you want to it's a 2D image, so if you want to flatten it, if you flatten it and we put as a 1D array, we'll get a 784 values. And then 48 channels we are keeping it, and then we are applying ReLU as activation function. Then we again having a second hidden layer with 48 as our input, which we are taken as output here, we taken as an input, and then we are giving us 24 as a 24 channel as a output. Again ReLU, and that last layer is a classification layer, where we are keeping output as a 10 class neurons, because we have a MNIST data set consists of 0 to 9 values. For that we having this, and this is the def forward is basically converting the image from 2D to 1D. So x.view will give us that, and then we are calling the self classifier. So this is a typical one neural network that we have formed, fully connected neural network, right? Now we haven't applied here batch norm here, but here we can apply batch norm. So in the second, the same kind of network we have created, but here we are adding the BN, that is batch norm, right? So how we are doing it, everything is same, only difference is after applying the linear layer, we are applying first batch norm 1D, because we are taking the 1D array with respect to, so we are taking 1D array, that's why we are applying batch norm on top of that array. That is after taking 784, after converting the 784 values to the 48 values, we are applying batch normalization on that. On that is here the pre-activation is coming to picture, pre-activation function, and then we are applying the activation function here, that is in the term of ReLU. Then again the second layer, on after the output of second layer we are applying batch norm 1D and ReLU. So this is how you can define the batch normalization, and it will come as a one single layer on top of that. Same forward is like this. If we run this now, if you try to print your model, how it look like for without batch normalization, this is without batch normalization, and this is mynetBN is with batch normalization. Okay, so you can see how our model is in place. First is a linear for without batch normalization, followed by ReLU, again linear, followed by ReLU, again linear. Here they have only 5 layers. Here we have 7 layers, that is linear with then batch normalization, then ReLU, linear, batch normalization, ReLU, and linear, right? So this is how we like this. Now what we are going to do, we are going to compare the performance of these two models, that is without batch normalization and with batch normalization. So how we're going to do that, we are going to do that on our MNIC data set. So here we are keeping the batch size of 512 for we are doing the evaluation part. So after keeping batch normalization size equal to 512, then we are going to call the train loader using the toss.utility. So we are calling the train set, batch size is 512, and keeping shuffle 500, shuffling all the images. So if we run that, now we are defining loss function as cross entropy and optimizer for both without batch and with batch. Without batch normalization model and with batch normalization model. Okay, so we have keeping the stochastic gradient descent as our optimizer with model parameters as assigned earlier with learning rate of 0.01. Okay, now after this we are having two arrays of loss array for without batch normal model and the model with batch normalization. Okay, so we are assigning this loss B and ARR for batch normalization. We are going to run this model for 2 epochs, and for each epoch we are going to enumerate this data. That means for train loader, that means in each iteration, this is will come as iteration, each iteration we will train the model with 512 images because our batch size is 512 images. Okay, so we will take the data into input and label. For training the steps for normal models, you will put gradients for all the weights and as 0. Then you will calculate them, you will take the model and you will put this input and get some output. Then you will calculate the loss function, then you perform back propagation with loss dot backward, and after that you will update the gradients. Same thing will happen here in the batch normalization model also. Only difference here is your model name will be changed, right? And opt bn, all this underscore bn is batch normalization, so we are keeping everything as it is with respect to it. Then loss ar append, so after this and whatever the loss we are getting here with loss bn and the loss as a variable, we are going to append that in the array. Okay, now what we are going to do, we are going to print certain values. So this is for printing the output after every 10th epoch. So printing the um, print we are going to printing the plots after every 10th epoch, see 10th iteration, my bad. So I hope you by now you clear that iterations and epochs are two different stuff. So let me run this before explaining this part. So let me run this part and I will show you what the output look like. Okay, I think I haven't. Okay, let it run and I will show you what it look like, or I will show you the topmost part. Okay, so this is the kind of plot that we are trying to plot here. Uh, so what we are doing here, they are overlapping the whole this thing. So what we are seeing here is actually the densities of weights. All the weights for each layer we are plotting them within this as a normal distribution to see that how it is, how much they are, how much changes are happening with respect to after each iteration. After every 10th iteration we are seeing that, and in the top we are we are just calculating that for loss at particular that moment. So the loss here for normal model is 2.31 and the batch normalization is start with 2.35. Okay, and this is the code I'm highlighting right now. So this is the code that we are writing for generating this particular plot. So let me just explain you this code and then we will see the actual out result what we are looking at. Okay, so now once the model has been trained for particular this aspect, particular batch, uh, so what we are doing is after 10th iteration we are putting our model into eval mode. Eval mode means after training to keep that into to keep it as a testing part. So for that we use eval as a function. So to keep that, so we are putting eval as a function. So now the PyTorch know that now we are using model to uh, for the evaluation purpose. Now what we are doing right now, we are giving now directly we are we are trying to see that how weights has been changed over the three layers, that is 0 1 2. So what are these three layers? So let's see what is there. So input is the input image, and we are now whatever the train classifier we are having, that is the first layer, we are passing that and we keeping the storing the weights at A. Now the same A will be passed to the layer 2 and see that what is the output. So that output will be taken as an input at the model or classifier 2, and again we pass as an input and we get some output, and this output of A we are putting as a 1D array, that is the whole as a 1D array, and then we're trying to plot this uh, here on this curve. Okay, so that is the what we are trying to do. So what is the classifier 1 2 3 4? Here you can go up and you can see here that this is classifier 1012. I'm highlighting right now for the model without batch normalization. We are printing the weights value for linear, that's the first layer, then ReLU, activation function, and the second layer, right? Similarly, in a similar way, uh, we are print we are storing the weights value. We are trying to present the weight values of 0 1 2 3, 0 1 2 3 layers. That is 4 layers we are doing it because we are adding the batch norm equivalent to that. Okay, so I think that is the correct part. Oh, till 4. So till the second batch normalization part, till this 5 layers we're printing the weight values. Okay, so we are just checking the density of those things. So after every 10th epoch, what we are saying, this is for 0th epoch, our loss is 2.31, a loss with batch normalization 2.35, and this is how our weights will look like. Okay, now what happens after 10th epoch, 10th iteration, my bad, after 10 iteration, what is happening that you can see that our normal the weights are normally became very shrunk, and it is between 0.25 to 0.25. Okay, however our blue graph, which is with batch normalization, it has been quite spread out, right? So let's see for 20. So it has become more and more thinner for the normal batch loss and so normal model, and the weights for batch normalization has been spread out. Okay, now here also the loss, you can see that the loss with batch normalization has been decreased compared to the loss of the normal model. So like with 38, you can see that it is the red part of the thing is becoming shrunk, and the green part has been flattening out a lot. So like this we have taken for 50, 60, 70, 80. Let's go till end. This is for 100, 110. Okay, so till here, so till 110th iteration, so we are getting at the last iteration we are getting that our model has become spiked up, but with respect to our batch normalization, it has been quite spread out. Now what is the effect of batch normalization? So we are plotting this curve with respect to the loss function. So for each iteration we are plotting the loss value, and you can see the green one has been reduced drastically compared to the normal model with respect to this. The same has been done for another epoch. This is now the start for another epoch, and we can see the loss of batch normalization has been reduced quite drastically. So the reason so how you can explain this phenomena is that when you're dealing with batch normalization, after each and every epoch you're stuck with only certain ranges of values. Okay, with only certain values. Because of that, you're not able to come out of it. But what happens with batch normalization is, after you're calculating any value, you're applying normalization. So because of that, the amount of data that you want to learn about is pretty good, because you're not fixating on a certain point. It bringing noise into the picture, and because of that, you can see that the green part is pretty spread out. Even the value of that is pretty low, right? So that is the help of the batch normalization, where it is bringing the noise. It is acting as a regularization, so a regularizer, and because of that, it is prone to avoid the overfitting part. Okay, so this is what about batch normalization. It is helping us to remove lower the loss function, um, compared to the without batch normalization, and it's helping us to learn and make the model more and more robust with respect to it. Okay, so this is the first concept that we are looking into. The second concept is dropout. So what we'll do, we will maybe take a 5 minutes break, or we can have a question, uh, and then based on that we will take this dropout as a second part. Okay, so the question is there any neural network that is not feed forward? The word just seemed to mean signal flows from input layer to output layer, which always happen. When there is a back propagation, depends on whether they are hidden layers or not, but even there's a feed forward neural network. Yes, the CNNs are not feed forward network. See, feed forward, concept of feed forward means, uh, you should not take it as an architecture. Usually when we say feed forward, we consider as a fully connected layer. So let me show you what is fully connected layer first. uh, See, this part will be there, fully connected layer. This part will be present in almost all the type of architectures where each neuron is connected to each other, right? But its computation is very, very high, right? Feed forward means I'm going from lower layer to higher layer, kind of like that. So that's a concept of feed forward come into picture. Now, what is convolutional neural network is little different. Here the concept of filters come into picture, which reduce our number of computation to a very much higher level. So convolution layer max pooling, so this is something very different, and what you assume as feed forward is something you can see in this image at the last part, on the rightmost part, where the green and red dots are there and each node are connected to each other, right? This you might be considering as a feed forward, but it's a fully connected layer. And feed forward, you can considered here this part also, where we are taking one input, we are applying certain transformation and again giving as a second input, like that. So this is in the context of feed forward will be, you can find it in any other architecture as well. It's just that one input is going above and above, and back propagation is based on the whatever input you're learning, you just trace it back to change the weights based on the loss function. So that is a feed forward as a concept, but architecture wise multiple difference are there. Now after this, from tomorrow, we will look at something called as recurrent neural network. So now here the architecture is totally different. Here the architecture will be totally different from what we have seen in convolutional network, right? So we will see it tomorrow. Based on that, based on which I can tell you much better. But feed forward as a concept is pretty straightforward, that it is there in every other architecture. It just has a concept that I am moving my data to upper layers or the hidden layers. Okay, any other question? Okay, so let's take maybe by 7 o'clock will come and we will see the dropout concept, and based on that we will we will see ML flow as a tool which you can use. I'll just introduce the tool, maybe in next session or maybe some other session I will show you how to use that also. Okay, um, so let's take 5 minutes break. We'll come back by 7 o'clock, and if you have any question, please type down in the chat box in the meantime. Okay, so welcome back. Um, so I think SK is again. Okay, so the first part is so with respect to following this thing that what is the meaning of feed forward network, and if we are talking in terms of signal flow, how it is dealing with. So he's saying that um, no deliberate signal loss or distortion is happening due to architecture. Actually, that thing is actually totally opposite of that. Because of the architecture, a lot of signal loss and distortion is happening because it's trying to learn the, let's say, image from multiple different angles with respect to it, right? And every layer is not a full representation of the signal. Actually, uh, it is full representation of signal. Yes, you can say in a very different way, like every layer transform the input in a such a way that you, as a humans, we can't understand it, that what that layer is actually meant to do. Okay, let's say convolution layer. In convolution layer we have multiple filters. Each filter will do its own work. For example, a filter can detect an edge, a filter can uh, make an image only into grayscale. If it is in 3 RGB scale, it can make to grayscale, like that, right? So it is so multiple filters can do multiple aspect of that, and that is something we can visualize it, what each filter can do what, but we can't state as it like we can't state that it is not distorting. It is distorting it, but again try to, so what it try to do is, based on distortion, try to see that the distortion is making sense to reconstruct the same image or not, right? So in a partial sense, yes, it is trying to have a full representative image, but in a very different way, okay, which is something we can't explain it as of now. Okay, and then you're saying that at every layer we have full representation of signal modified only by linear transformation and non-linear activation function is equal to feed forward. No, feed forward is, as a concept, is only transferring the input from the input layer to the hidden layer to the next hidden layer till you go to the output layer. Apart from that, there's nothing much as of the see, non-linearity is come into picture because if you put everything in the linear function, which is w into x as a transformation, it's not giving to give us some meaningful value. It will only try to fit a data uh, on a non-linear, try to fit a line on a non-linear data, right? So that is not possible. That's why non-linear aspect is coming to picture because of the activation functions. These are separate concept of the feed forward. Feed forward, as of now, you can just assume like that. The the by different, no, see, okay, feed forward as a concept is just moving the data to a certain direction, which we are saying forward direction. That's why back propagation come into picture. That is from the output layer, that is the classification layer, and whatever the loss value you are getting, based on that you are trying to find the gradients for each layer weights and biases of the each neuron. Okay, so that concept is back propagation concept come focus on that, that is trace back to all the weights to tilt the input and try to update it, right? Similarly, feed forward is based on whatever the input you got after back propagation, again it will force back to send the whatever the based on changes in the changes in the weights, again it will force back and try to see that whether the learn change after the changing the weights because of gradients, is it improving or not. So that is a to and fro is happening with respect to it. CNN, RNN as a concept, see in normal fully connected layer, you're just passing the all the neurons and stacking the neurons side by side, right? But in CNN, you bring the concept of filters, which is not there in a typical fully connected layer. Filters have certain specific job. Then there's something called smack pooling that do something specific job, right? That specific job that they're doing is not something you can find in a fully connected layer. Let me again share the screen again. If we can show side by side. Okay, it's happening now. So recurrent, okay, fully connected, and convolution neural network. Let me see if I can get an image side by side. Okay. Um, Open image in new tab. Okay. Here, CNN as an architecture consists of something called as convolution layers, something called as pooling, and then something called as fully connected layer. It's a different architecture together because the components here is different. You might be assuming this fully connected layer as a feed forward network, okay, which is true in terminology, which we call it as feed forward network because its path is like this, but there's something called as backpropagation is also come into picture. So that's why we don't use that word, we use fully connected layer. Okay, but as a concept wise, just like you can see, this is a zebra, and from zebra it is going moving forward, right, transforming. So CNN has this certain component which you can't find in this fully connected layer, so that's why it is different. In RRN some other component will come into picture to replace that part. Okay. Okay, you have asking, it seems the definition of you is somewhat arbitrary and dogmatic. XYZ are feed forward, but ABC are not feed forward. It's completely new architecture were to design, one might not able to decide based on definition whether it's feed forward or not. Uh, no, kind of not like that actually. Like again, I'm saying, maybe repeating this. Okay, let's see, maybe if I'm wrong. Let's see what do you mean by feed forward network. That will be much better for us to understand. This is Wikipedia. See, it is characterized by the direction of flow of information between layers. Okay, so it's a basic flow of layers. So any layer in any architecture we are talking about, we are not dealing with the architecture. CNN is the architecture. The architecture can be changed, but its component will be same. You can increase or remove the convolution part, pooling part and all. But feed forward is mostly about any architecture can be a feed forward network also, because you're defining the flow of a particular input to a certain direction, right? Let's say you say the left to right, it's a one direction, right? So that is the concept feed forward. So you can actually say any network as a feed forward network, but that is a quite a vague on this thing. We can't actually define this part, so that's why we have to we have to say something called, that's why we are coming with recurrent and the CNN part, because it has something called as convolution layer and the pooling layer. Feed forward in general, it is like moving to a certain direction, particular direction. It is unidirection in this case. Still not able to understand? Feed forward as a concept, we just check. It's a flow of information from one direction to another direction. If we just keep that in mind, any neural network that you're creating, either CNN, RNN, or the transformer, everyone you can call as feed forward. You can just say it as a higher abstraction layer, but not as a particular layer. Feed forward comes under CNN, RN, every single, even transformer also, even in LSTM also. So that is totally justifiable based on what you're saying. But at the same time, the architecture we are talking, when we term of architecture, we will say CNN and RN only, not feed forward. Okay, so if not fully, maybe after the session, this session dropout part is over, then we can discuss properly, such that maybe I can maybe able to understand what in your mind it is going on. Okay. Okay, so let's start with dropout part. So let me stop presenting this part. Okay, so now let's go back to another concept called as dropout. Okay, so what is dropout in as a concept here in the neural network? So for that, before that, let's understand what is something called as ensemble method. Okay, so let's talk about ensemble method. So what do you mean by ensembling? So in a machine learning field where we're using linear logistic regression. So okay, let me try. So there's something called as input, and there's something called why is input and output is there, right? So what I will do, I will create some classifier. Let's say I want to create some classifier. I may use LR, which is called a logistic regression SVM, and something called naive bias. Okay, so I'll give them as an input and output. I will try to learn something from this layer. I'm getting some output from YLR, YSVM, and YNB, and then I will do some kind of aggregation using polling, voting, or simple averaging. Based on that, I will get some final output. Okay, so what I'm doing, I'm combining the output of multiple ML models, okay, to give me final output. So it is like this, right? So I want to decide something, that which career I want to choose. So what I will do is I will ask 2-3 people, right? And based on that, I will try to see that if everyone is giving same kind of some same kind of advice, I might choose that particular advice, right? Similarly, let's suppose that I'm giving the Fibonacci data set here with particular labels 0, 1, 2, 3, and my output is saying that LR may be saying that with 80% confidence that the output of that image is 1, but others are saying that with the confidence of like 0.8, and others are saying like zero point 0.3 and 0.2 with confidence or probability that my output will be 1, right? So when I aggregate it, I might get 0.4 parts something kind of, if I take just simple averaging, right? So what I can say that I'm still not so convinced that whether the given image is particularly 1 or not. So I'm taking the advice from multiple model here, and based on that I'm aggregating my output, right? So that is a simple ensembling method is come into picture for machine learning, right? Now machine learning is basically very specific because we are handwritten, we derive the equations already, and we don't have to learn anything. We don't want to learn something on its own. We don't want machine to learn on its own. We just need to learn the correlation based on the equation that we have provided, and that is why ensembling method is from the ML perspective, right? So now the natural question that we can arise is, now coming with respect to the deep learning, so can we take can we perform an ensemble like joining multiple machine learning models like that? So can we apply ensembling on neural networks? So this is what a typical question that we can ask for. Okay, so we might get two kind of option with respect to the ensembling of a neural network. So let's say option one is that so option one is train different architecture, or let's say models here on the same data. Okay, so let's say I will say I have this model. So kind of like this, some one model, this is the architecture one, arc one I'm saying. Then there might be another architecture like this. So this might be fully connected in this case, and this is second architecture, right? So I can have multiple architecture with respect to the uh, this training the different architecture on same data kind of thing, right? So I can define as many architecture I can want, because based on that I can have multiple layers, multiple hidden layers, and hidden layers I can have multiple different type of neurons, right? This is option number 1. Now option 2 will be um, train on same architecture but on different subset of training data. That is like kind of batch sizes that we have seen earlier. With different batch sizes, I can try to learn on same architecture, right? These are two options that pretty much available to me, which I can do upon. I think one comment is there with respect to this. We can only use output of model as input of second model, like first being regression model as output of one. Okay, so when you're talking with respect to ensembling method, we can't give the output, like let's say, okay, let's say for a regression model, let's take one regression model, right? You are saying like this. So from logistic regression, I give that one as output to SVM. Unfortunately, that is not how it is going to work in ensembling method, because you're giving output. Sorry.
Much like ensemble stem, what if we take the output the right way? Maybe like max voting or something.
Yeah, that is there once I'm getting the output from all the models, and then I'm doing aggregation voting. That is, I'm doing on the y value, not on the here as a particular model. I'm not giving output of one model to another model. I'm not doing like that. So it's like I'm making some small machine learning models, and then I'm aggregating their outputs together.
Output, yeah, got it.
Yeah.
Got it. Thank you.
Yeah. Okay. So now we have seen that for neural network, if I want to take this to neural network, I have two options, that I can define multiple architectures. I can define multiple architectures, or I can define same one particular architecture, and then I will try to run on different training subset of data set, right? But it has one major problem for both of these problems, that it is quite expensive in nature. Now, why it is like this? So let's say I have 10,000 data points, right? So if I'm trying to learn on different data architecture, let's say 3 different architecture, it will take maybe one architecture may take 5 minutes, one architecture may 10 minutes, one architecture may take 8 minutes, kind of like that. So it is quite computing resource thing. So the higher the data, having different architecture doesn't make sense to me, because I'm using multiple resources on top of that, right? So that is one point. With option number 2, what is happening is, even though I'm keeping one architecture, the architecture I can make it complex, that I can have a very big complex architecture with 5 or 10 layers and on, like, and on top of that, even since the deeper the model is, that more time will take it. Even though you're taking subset of data, it will still take a lot of time to process it, right, to train on the each subset of data. So here my computing resources are still taking a lot of time. So it will consume lot of computing resource it will take, right? So, and also so once we know that this is a lot of this part is there, so can we do something with respect to let's say, no, maybe not with the option, but can we do something with respect to option 2, right? Because having training different architecture is still pretty consuming. But here, if we can tweak something, that if I take same architecture, can I do something with respect to it? Can I make with same architecture, can I make this architecture 1 and 2, can I do certain tricks with respect to it, such that I can reduce my computation resources, at the same time I can keep my training robust, right? So here the concept of dropout will come into picture. So like so what we can say here is, let's say I have, okay, this is the kind of model I'm having, this is my original model. What we are trying to say in dropout part is, so during the learning, this is the input will be as it is, but during the hidden layer part and all that, or maybe during certain nodes, what I will do, certain neurons, I will not use them. Okay, so let's say this. So wherever whichever nodes I'm crossing right now, I'm not going to use them, right? So So this is concept, not using this nodes considers dropout of particular nodes. Okay, so that is one way of this can be my architecture one, kind of like that. In another architecture, sorry, yeah, in another architecture, I might not take certain inputs. Okay, I might not take certain outputs, and I can do this is considered my architecture 2, right? So what do I mean by architecture 1 and 2? The nodes which I crossed right now, I'm not going to consider them at all. So this is how I can play with my one architecture, I can do with another architecture, keeping everything into keep deriving anything from the original architecture, right? But again, we can similarly argue that even if I taken two different architecture with respect to the original model, still my chances of uh, since my chances expensive will be still there, right? Because I do need to train the whole data set on all of these architecture 1 architecture 2 like that, right? So that again still the expensive problem will still persist. Okay, so what we can do here is, here we can use something called a trick here. So trick come from the perspective that even though I'm taking multiple different kind of architecture, I can I can share my parameters across all this neural network, all these neural network. So whatever neural network I'm getting, I can share certain parameters to each other. How we will see that? The second trick that we can do, we can deal with is that along with this is sample a different neural network for each training instance. Okay, so what do we mean by with respect to these tricks? Okay, so let's go one by one. So what I can say, let's say first deal with the sharing parameters across all the neural network. Okay, so the conceptually what it will feel like, I have this original network. Okay, this my original network is there, and this is my at particular instance I have one network here where I am crossing certain nodes which I am not going to learn with respect to this, right? Only one architecture is there. So based on that, after one iteration or after one epoch, okay, one epoch, I will learn certain weights for these particular neurons and all that, right? I will learn certain parameters with respect to it. So what I will do during the second epoch, I might I have this ability where I can change the architecture. Okay, so in this case I will, let me again make this and use different color. Now in this case I might uh, I might remove these three nodes, cross with blue, and what I will do, whatever the weights which are common to me, let's say this part, this upper part, this from input to hidden layer 1, this is very common to me. Even from any input layer to this particular layer, I have these weights. So I will take these weights, whatever the weights will be, let's say W1, I can assign this W1 weight to here. I don't need to learn it from scratch. I will not initialize it again. I will take it from this weights and I will put it here, right? Similarly, so whatever the earlier weights which I have taken, I will if there is a commonality between the part 1 and part 2, neural network 1 and neural network 2, I will take those weight. So this is for me weight sharing. This concept is called as weight sharing. Okay, so at each epoch, if I'm changing my neural network architecture by randomly taking assigning a neural network, based on that I can, and if there's a commonality between the previous one and new one, I will just take that weights and put it, assign it to that the newer neural network automatically. Okay, so how can I do this? So is there any particular procedure for to do this part? So a kind of procedure is there. Just conceptually, just let's discuss this point. But there are multiple new ways are there. But what else how neural network can be drop out? How certain nodes can be drop out, right? So what we can do here is we will take some random seed okay, and we will say that it will give certain number for each neuron, okay, and we will giving a threshold that any if the random seed value is greater than 0.5, I will keep that neuron, otherwise I will keep the neuron in the network. If it is less than 0.5, just remove in the network, remove from the network. Okay, so that's what we are doing here. We are just removing from the network, removing that particular neuron. When we are saying removing from the network, we are not exactly removing from the network. It means that the whatever the weights we are calculating here, right, with respect to this particular weights, let me denote with particular green part, right. We are here during the back propagation parts, all the whatever the values we are doing here, the weights here will be constant, right. So because of the constant weights, what will happen is I will not I may not get the delta W of with respect to that particular grade. I will not get the gradient value with respect to the particular nodes. So because of which my gradient after back propagation, my weights will not update. Weights will not update. Okay, so this is what happening in this case, that yes, I'm doing weight sharing wherever there's a commonality between the earlier neural network and the new neural network. I will taking that weight as it is, but for the one which I'm seeing as dropout, I'm not removing them, I'm just keeping them, but I'm keeping in such a way that when I'm doing backpropagation and all, I'm not changing its weight and all, because I'm keeping the value as a constant. So when I'm taking a partial derivative of that weight with respect to loss, I'm getting zero value. Because of that, my weights will not get updated. So that's the concept of dropout within with respect to each neural network that we are doing. Okay, so it will be like so if we want to have a particular algorithm with respect to it, so we will say initialize all the parameters, in this case the weights for each neuron. Okay, now we will iterate over data. Now in each iteration, what we'll do, we will take x and yi, that is current mini batch. We will not take whole data together, we mostly take with respect to the mini batch. Once we do that, we define a neural network. Now new neural network will be dropout network. Okay, so like just like how we are saying, right, with certain probability. So then we compute the loss with respect to the network, where we're passing the network xi and yi, and then we are back propagate for the particular particular network, and then we'll do this till we satisfy. Okay, so this is what we typically do. For each maybe batch, we might create a different kind of network. Okay, now once this part is there, that okay, let's assume that randomly it is assigning maybe creating a random seed to select a particular kind of neuron, right, with 0.5 greater than 0.5, keeping the node, less than 0.5 not keeping the node. All this is good for training part. What about a testing part? Okay, so how, let's say, how dropout work during testing. Okay, because this is, since all these are random part, so we can't just again we are not since storing all of this network again somewhere, we're just sharing the weights from one side to another side, right? So we are not keeping track of all those things. Practically it is impossible, because if you want to keep for 10 different dropout network, it will be pretty much computationally very much expensive, which we don't want that, right? We're trying to avoid that computationally expensive resource, right? So what we basically we are doing is, if we have a particular network like this, the network that we are defining here, right, it is assigning a particular probability here, assigning probability to each node or neuron. So what do we mean by that? Okay, so in PyTorch, okay, before PyTorch, let's say if you have four variable, right, x, y, z, sorry, yeah, u and v, right, we have four variables. So if you assign 0 and 1, 0 1 concept, like that, so we can get 16 combination where everything is 0 0 0 0 0 1 0 1 0 1, kind of like that, till 1 1 1 1 1. So we have 16 combination kind of like that, right? So for each part we have assigned certain probability, that is to come to this part, selection part, I have probability of 1 by 16 kind of this, right? Or I can say that for for places where x is equal to 0 is 0.5, right, where y is equal to 1 is 0.5. I have certain probability associated with it if I look at this truth table, right? Similarly, here if I'm looking at each and every neuron, I can define certain probability, that what is my probability of having this neuron in different neural network when I apply dropout. Okay, so if I say the dropout equal to 0.5, if I assign this as a value, actually we do that in a PyTorch. If we assign this value, that means all the neurons will come at least 50% of time while creating the every different architecture. At least 50% of time they will be activated, and 50% of the time they might be disabled, like that. So this concept probability will come into picture, and once we are defining certain probability to each and every network, so what is happening, so this is my neuron, and based on that I am getting certain weights, right, w1 w2 w3 and w4, right? So what we typically do, we'll take that weights as it is. But now because of dropout, okay, my this neuron might not be always present. So, and my probability that this neuron will be present in the neural network is probability is equal to 0.6, let's assume. So what I will do, I will assign this p value and I will multiply with its weights, because I'm not getting the full architecture, I'm taking parts by parts of the architecture. So I'll assign the probability of this neuron with its own weight. So whatever weight I'm calculated for this particular neuron, I will assign the probability on that, and based on that I will calculate the whole architecture. Okay, so this is the concept of neuron during a testing, where each neuron here, each neuron I am taking, it has assigned certain probability, and because of certain this p value, I'm calculating its weights based on the p value. Okay, such that when I'm giving an input during testing, it will consider this probability of p value, that whatever the weights are there, consider that for 0.6 of that value, right? Because I know that this 0.6 value for the 60% of time this neuron was active, so please consider its value as 0.6, like that. So because of this you cannot test it during the testing time because of this probability value. Okay, uh, okay, let me see, a lot of discussion was happening during this. Let me see if you have any question. Yes, it's equivalent to bagging, but the concept here is kind of different. The concept as it is same, that you have to take out, you will take certain nodes from the random, for if you're taking a random forest, right? So you have to take out certain nodes, or you will take only few set of nodes, or you will consider only few set of features like of that. So it is exactly kind of like bagging or ADA boost here, but here the in neural network context it changed little bit here and there. Okay, now checkpointing is okay. So now checkpointing is different from dropout part. So what I mean to say is, this checkpointing you can do between wherever you get the best model. At that point you can save that model using checkpointing. That is well and good. But here in dropout, we still not know which part of the model, which version of that neural network is best for us, right? Since we don't know that part, we can't. It's not a good idea for checkpointing this. Oh, for testing data. Mm, For testing data, should we do checkpointing? Why you need to do for testing data? Here I'm not regenerating any of the neural network. Whatever I did for the training part, I'm not regenerating it. That's where the probability part come into picture, that I'm assigning particular probability for all these neurons. So I'm not generating it. So the whole I will keep this whole network as it is with certain probability for each neuron. So here the checkpointing concept will not come. Checkpointing comes only during the training part, where
See,
yeah,
see,
please.
I'm just asking, right? Thing is like here, right? We'll be having so much of model because of a dropout, right? We'll be having so yeah. For example, my training data will be trained on 5 to 6 models based on the value of dropout, right? We will have different models. So different model will produce some different results. Yes or no?
Yes.
So so thing is right for testing data. If you present any unseen data, so whichever model is best, can we whichever model parameter is best, can we use that for testing data?
No, that's where it is coming a difference here. See,
Okay.
whatever the, let's say this is the original architecture, and I'm, yeah, like say you're from this through certain combination, you're defining some 8 models out of it, right?
Yeah.
Now what is actually happening in the scenario? I'm calculating this value, whatever the weights I'm getting from each of the model. Again, I'm passing back to the original model itself.
Okay.
I'm not
I see.
storing it anywhere. Okay. Okay, now let's see the code of this part of dropout. So again, let me classify. The dropout concept came from the perspective of ensembling, like just like bagging and boosting from the ML concept. But the concept of having, since a machine learning model is typically small compared to a deep learning model, so it's okay to have multiple models and combine them together. But for a neural network, the parameters are quite high, so we can't have different architectures combined together, right? So what we have to do, we have to do some trickery on this. So what trickery we can do, we can take a one original model or original architecture, and from that we just remove certain nodes out of it and play with that, and apply the particular, give the input to it to see that how the weights are learning. Okay, and then after that it will do for multiple different type of architectures, by removing certain nodes and all that, and based on that it will calculate the weights. The beauty of this is that I can share the weights across different architectures. So whatever I learn from the architecture 1 model, I will pass on to architecture 2. From architecture 2, I will pass on to architecture 3. Once I'm able to do that part, after each epoch, once I'm doing that, I'm doing the weight sharing part. So I can find each and weights for each and every node, and I such that I can get a full model to me. Now what I will do during testing time, I will take that whole model with weights, everything into the picture, and I will keep it for testing part. But the only difference is, as I know that all nodes are has not been used for each and every in kind of input, right? So I have to give certain probability of the nodes, that, and I don't know for which node works better for which kind of input. So what I will do, I will just give a probability that this node has been present in 60% of the architectures that have been created during the dropout part. So I will give 0.6 or 0.8% of value, and I will calculate that with its weight. So it will get certain weightage, that how much weight should be given to from the particular node. Based on that, I will calculate my input. So I will calculate my output based on that. Okay, so this is there. Now let's see the code to see that how it performs when we apply the dropout part. So let me share the screen here. Let's go to collab notebook again. Okay, so to understand that how it will work, let's take a simple data. Okay, so based on that we can understand it much better, because dropout is also a type of regularizer. That means it's helps to introduce noise and avoid overfitting of data. Okay, so this is the specialty of dropout. So what we are doing is we are taking a random input. So we are taking this input where so what we are trying to do, we are creating a situation where we want our data to get overfit, right? So how it can get overfit? If I give a simple data just like this, so here you can see that if I fit a line, that should be more than enough. But if I, for the simple data, if I give a very complex model, that is a particular neural network model just like this, I might get to overfitting of data because I will try to capture each and every part of the model of trust and train, right? So this is I'm doing. So how I am doing this, I am defining number of points as n. Okay, I'm defining certain noise here. So what I'm doing, I'm taking x train. So using the torch.linspace, I am creating 50 data points with equally space. Okay, then for y train, I am introducing certain noise based I will take the input training input and adding certain noise using noise dot toss dot normal. So I'm introducing certain noise with respect to that. Okay. Similarly for test, I'm creating some random equally spaced input, and phi test as introducing certain noise. And if we try to plot this data using plot plt.scatter, this is how it should look like. So it's just typically a simple data where we are trying to, if we can fit a line, that should be more than enough for us, right? But now let's see what will happen if we try to give a complex model, that is a neural network, to try to fit to this data. So what we'll see how it will work. Okay, so so here we are NH is the number of hidden nodes in a hidden layer. Okay, so we are defining here 3 hidden layers with final layer, which tells me that what is the output. So it is a kind of regression equation, not as a classification, where I just give a x value and it has to identify the what is the y value for me. Okay, so this is a simple with respect to x and y value is there. So I have this one model where only I have linear and the ReLU function, activation function, and I have another model where after defining the linear layer, I'm introducing the dropout. So you can give dropout as dropout like toss.nn.dropout, and I'm passing that 0.2. That means only 0.2 or maybe 20% of time node should not be present, right? So 80% time the node will present, 20% of time node will not be present for each neuron. So for each layer I'm providing 100 neurons. So so I am saying that out of 100 neurons, every time only 80% neuron will be active at a time, right? So similarly I define second dropout layer also based on the linear aspect. Okay, so once I am able to do this part, and finally I have a output as 1, where at the final one neuron I am passing my y value, which is I am trying to predict it. So I have two models with respect to it, without dropout and with dropout, and using toss.optimizer I am calling the Adam optimizer with learning rate of 0.01, and for dropout the same Adam optimizer only with same learning rate, and the loss function is MSE loss, that is mean square error. So let's do this. Now what we're doing, we're going to run this earlier this data what we are seeing here for 1000 times. Okay, we are going to see the data 1000 times, and what we're going to do is, this part is for the model without dropout layer. So we'll have a model. In that we just give the input and we'll predict the output. Based on that we'll find the loss. Based on the loss we will calculate the gradients. See, we'll keep gradients as 0, then we'll using back propagation we will identify the gradients, and then we will using opt-out step we will update the weights. Similarly for dropout layer or dropout model also we are doing the same thing. Now what we are doing in this part is, after every 50 epochs we are going to plot the data, that how it is fitting, how each model with without dropout or with dropout model is trying to fit the data. Okay, so that is what we are trying to do. So to do that, we are bringing model to the evaluation part, so that we are telling the model now, instead of training, you should evaluate now, right? To evaluate now, it will give test data, it will get some prediction on test data, and based on that, using loss function, will get some loss value. Similarly for dropout model also same thing. Now we will, based on this data, x train x data, and with respect to the our prediction data, we are going to plot the values. Okay, and for each plot we are telling that what is the test loss for model without dropout and with dropout, and we are plotting it. And after every model, we are asking the model that, okay, now evaluation is done, again you go and train, because it is coming under similar for loop. Okay, so let's see how it is happening. Okay, now here at 0 epoch, a loss of particular model is 0.16, let's say 16%, and loss with dropout is 90, that is much higher, right? So as we go after every 50 epoch, we can see that red line is the normal model and the dotted blue line is the dropout model. It is trying to fit the data, right? So as we go after every 50 epoch, we can see that red and blue is kind of overlapping to each other and trying to overfit the data, because it is, you can see that wherever the blue lights are there, based on that it is trying to there's a lot of curves are happening rather than having a straight line, right? So as we go down and down, let's go down, you can see that now more and more curves you can see on a red part, not that much in a dropout part. Okay, and here also you can see that the loss with dropout is reducing drastically, that is come to 9%, or here as a 10% kind of thing. So it is doing like this, and here at the 950th epoch you can see that it is almost kind of overfitting. It is trying to the red line, this normal time, is trying to try to capture all the purple points by trying to create a function which can take this non-linearity into picture. And similarly, if we try blue point also trying to follow a similar kind of path, but not as apparent as a normal model, right? So it is trying to maintain this part. Okay, so here also we can see that loss or dropout has been increased, because it is also trying to overfit this model. So what we can do here is, let's go to the code here above, and instead of dropout as 0.2, let's say 0.7. That means for 70% of the model, so we are making it less complex. That means we are trying to keeping the model shut for 70% of time for most of the neurons. Okay, so let's run this code again. Okay, let's let it complete. Will take some few minutes of time. Okay, so by the time, yeah, it is almost done. Okay, so what I have done is, now I have dropout layer, I have reduced it to 0.2 to 0.7. That means 70% of the time my nodes will be inactive for me. Okay, so let's see, if I make more model nodes as inactive, that means I will make my model less complex, because the number of parameters it has to learn, it will be less. So that means the blue dotted line will be mostly like a straight line, not as like a overfitting which we have seen earlier, or the way the red line has been overfit, right? If we have seen the red line is overfitting and trying to capture each and every point by having a lot of contours in between, right? So not of contour, lot of up and down part in between. But here in the dropout part, it's also trying to trace the same way up like that. But if I reduce the complexity, that means if I make most of my nodes as inactive, let's see what will happen. So if you can see that after 50 epoch, it is still a kind of straight line for a blue part, and for the normal part, it is trying to learn more and more the purple parameters. And similarly going, let's go a little below at 500. Okay, now at 550th epoch, we can see that even the loss are kind of for same, almost similar for both loss with dropout and without dropout. But you can see how the red line is trying to fit this purple point, and how the dotted blue line is trying to fit the yellow points with respect to each other. It is still a kind of straight line, not much difference, but with the red line it has been changed a lot of peaks and minima is coming to picture. So the reason we don't want this kind of loss up and down for this is because it leads to overfitting of data. If I keep it on for 2000 points, there's a high chance that I will try to trace out all these points one by one, right? But if I trace out for all the training point of overfitting, I'm not able to do it for testing. So right, I need to balance both the training and the testing loss, right? Which is dropout is helping me to do is helping me to achieve that part. So let's go to the last part. Here, as you can see, the red line is still trying to overfit the part. We're trying to have lot of curves and here, but still the blue dotted part, because of dropout, because we make the model less complex, we can see that how it is trying to fit the whole the training and the testing data, right? And the loss is not loss is still less, not that much less compared to this, but still it is. So you have to see the trade-off. Sometimes your loss because of overfitting, your loss can be high, but with testing but for testing error it might be less, right? So that kind of loss we have to overtrade, and dropout is one of the best regularizers to help with that. Okay, so today what we have seen is something called as we have seen the batch normalization to summarize what we have done. So we are using the batch normalization, and we have seen that it help it try to normalize the whole data, not only at the input level but also the hidden representation, and it help us to reduce our loss with the proper decline. Similarly, for dropout, we are trying to take multiple variation of the same model architecture and trying to reduce the overfitting part. Okay, so these are the two things that we have seen. Now another point before leaving I want to discuss here is, I want to show you basically, is something called as ML flow. Maybe tomorrow or day after tomorrow I will show the performance of the ML flow. So there's something now, once you're trying to code the deep learning models, all those stuff, right? That part is good, but the main challenge is not introducing an architecture. You don't have to introduce architecture. You will mostly use the existing architecture, but what you have to do is something called as hyperparameter tuning, right? So you will have lots of learning rates, you have lot of hidden nodes. Okay, you will have lots of alpha beta with respect to this regularizer. You have lot of different kind of optimizers, you have lot of different options, right? Which one to use? So that is the one part of this. What ML flow do is, so ML flow, where is this coming? Yeah, let me open it. So ML flow is a kind of tool. Okay, this is very small. Yeah, so what ML flow do is, it gives you a UI model where you can train your model on a different parameters, and you can check its accuracy, its multiple parameters, right? It will store all of these parameters, and you can compare the performance of different parameters, like you are saying checkpointing and all this, right? Even before checkpointing, you can just check it, that for which combination of hyperparameters my model is running properly. So to do that, I can use something called as ML flow, where I can see the whole life cycle of a machine learning part, and I can try to um, de deal with my parameters. It is one of the better ways which you can use if you want to tune your model to a certain place, and you have all the data with you. You just need to use the model ML flow for proper tracking of your different parameter, and based on that, whatever the parameter you choose found to be best, you can take that model and use that for prediction part, right? Maybe tomorrow I will show you how the ML flow works with respect to, I will just give you a demonstration with respect to that, so that it can get a better understanding. But one thing that you have to do for sure, that as an engineering part for you in any machine learning, deep learning when you're building a model is basically that you have to deal with how you have to tune your hyperparameter based on the input data, right, so that you can get a better accuracy. And we have a lot of option for that to track that thing. MLflow is one of the open source thing. Multiple other parts are there, but MLflow is quite open source, which you can use in your system, and you can try to see multiple aspect of your learning. With multiple metrics, you can define multiple confusion metrics. A lot of options are available to use this MLflow. Okay, it will help you to understand your model much better, and it is help you to show this, so whatever the changes you are trying to do in your model, that will kept in a particular table, and you can show it in that particular format to the anyone to, if you want to explain that how you reach to a particular kind of hyperparameters. Okay, so we will do this tomorrow for sure, but this is how I want to introduce that. ML4 is something you should try learning. Once you get accustomed to that, how you can train a model, any CNN, RNN, or transformer, now you should start using the ML flow as well. Okay, so that's the end the session from my side. If you have any question, please let me know. You can unmute and we can start discussion with respect to that. Otherwise, the session is end from my side. I'm stop representing. So please check out the ML flow for sure. So I'm just sending you this. Please look out this aspect, spend some time on this, and we can look at. Okay, so question, this ML flow have all various ML model implemented. See, ML flow is a kind of logging software. So whatever you have to define your models and all that, and based on that it will keep track of for each iteration, each epoch. These are different granularities there. Based on that it will create different models, right? So that models, it will keep logging of all this thing instead of printing it in our this thing. ML flow providing a much better UI for us to understand it. You don't need to feed dataset anything to ML flow. It's a logging. Everything what you're doing you will do on a typical notebook or Jupyter notebook or in a Colab, and then it will if you start ML flow, it will in the background it will check that which parameters are being right now used for training a model for the particular data set. Okay, is there any yeah, tomorrow is another TA session on from 6 to 8. That will be 11th TA session. Okay, any other questions? Yes, you have to write, but so let's assume like this, right? You will write you will have, let's say, 5 learning rates, 5 different type of hidden neurons for each layers, right? And maybe what else we can have? Um, let's say we can have learning rates, this part, and okay, we can also have something called as um, um, what else we can change? Epochs we can change. We can change the momentum, like if you're using a particular stochastic optimizes a momentum gradient descent, we can change the momentum part also in there. So multiple parameters are there, and you can just write as a nested for loop. That means for in that, let's even assume like that if you take only 2 nested for loops where you're just changing the hidden nodes and the learning rates, the combination will be, let's say, 5 learning rates values compared to for 5 hidden different 5 hidden nodes. So 5 into 5, 25 different combinations you will find, right? And you have to store that in a particular, in a such a way such that you can get all this output for each and every combination you want to create. You're training a model, right? So for that ML model is used. So changing different models is not that hard part. You just need to write a typical for loop that will take care of all the part. So code you have to write, it's just a logging device for better understanding. Maybe tomorrow when we see this, you might better understand that why it give a much better comprehensive visualization for finding a particular kind of for using particular kind of model It's like a kind of checkpoint. Even without checkpointing, you can use this part. Okay, any other question? Okay, I'm assuming there's not. So in that case, let's end the session today. Um, Thank you for asking the question. So tomorrow, again, 6 to 8 will come.